Alright, this recording is going to be for applications of exponential functions, so basically word problems that have exponential functions in them. We're going to talk about models of population growth, radioactive decay, compound interest, and the number E. And most of your problems for the homework problems are going to be, get that sign off of there, are going to be for compound interest. But I'll go ahead and we'll work anything that comes up on this PowerPoint for the other two things. A biologist is culturing bacteria in a large petri dish. She has 1,000 bacteria, enough food for the first 5 hours, so the population will continue to grow exponentially, doubling every hour. Find a function that models the population growth of this bacteria, determine when the population reaches 16,000, and calculate the population 2.5 hours after the scientist begins. So if it doubles our base, okay, we're going to, should probably be 2, but let's look. We know that we seek a function of the form PT, which is the population after a certain amount of time has passed. Our original population, A to the T power. The base is the fact. For A, it's going to be that it doubles every hour. That's where that comes into important. T is the amount of time. Alright, so they started with 1,000 bacteria, so that's our initial population. P0 is 1,000. So you're going to put that into this formula. So 2,000 is, after 1 hour, it's going to double. Okay? So 1 hour is your T, and it's going to double for an hour. So from that, we can figure out A. So we have 2,000 is equal to 1,000 A to the first. And so you're going to find out that A is 2, which makes sense for doubling. Okay, so now we have a function that models the population growth according to what they've stated in the problem. PT is 1,000 times 2 to the T power. And T is measured in hours. And they wanted us to predict it for 2.5 hours out, and they wanted to know when it would reach 16,000. So that's two different problems. So we want to know first the time for which it is 16,000. It goes from 1,000 to 16,000. So we're going to have 16,000 equals 1,000 times 2 to the T power. So you'll first divide by 1,000, so you have just the 2 to the T power on the right side. Okay? Now we're going to try to get a common base. So 16 is 2 to the 4th power. So 2 to the 4th is equal to 2 to the T. Well, we have the same base, so T must be 4 hours. So in 4 hours, we would reach a population of 16,000. Okay? Now the next question is, what is the population at 2.5 hours? So we're looking for PT this time. Okay, which means you have 1,000 times 2 to the 2 to the 5th, and we have calculators that we can use, and so you do 2 to the 2 to the 2 to the 5th, and the way you would enter that in your calculator, you would put in 1,000, and you would probably hit times 2, and then you can use something like that. It looks like a carrot top, little exponent, and 2 to the 5th, and then hit enter. And that should give you that number. Okay. So when we plug all that in, you're going to get, in 2.5 hours, you have about 5,657 bacteria. Okay, so usually with these application problems, there's going to be a formula for you to use. Okay, I didn't want to do that. Let's go on to the next one. This is radioactive decay. Decay has to do with half-life. Things that give off radioactivity will have a half-life, and they'll revert back to a more stable chemical in however many years or however many seconds the half-life is. Ancient artifacts are used with carbon dating sometimes, or some sort of something that has a long half-life. So determine the base. So the function A, T, that's the amount at the end of a certain amount of time, is equal to the initial amount and your A to the T power. And it's a half-life, so that's going to be 0.5 to the T power. but we'll figure that out. Solution, okay. A0 represents the amount of carbon at time 0, and we're looking at how much it might be at time t. And it's going to vary, and all these things are going to vary depending on the details in the problem. So here's our problem. We know that half of the original amount of carbon-14 decays over a period of 5,278 years. So A, 5,278, is half of A0. And that's going to give us our equation. A to the 5,028 is equal to A0 divided by 2. And that's going to equal A0 times A to 5,728 power. Okay? So we want to solve it for A. We can first divide both sides by A0. Okay? And so when we divide by A0, we're going to cancel it out from the equation. And so it really, that tells you what they're saying is it's irrelevant in terms of solving the original equation. And we're left with 1/2 equals A to the 5,728. Okay? Then we're going to find the 5,728th root of both sides, which that of A, we're just going to have A, and then 1/2 to the 1 over 5,728 is 0.9999989, or basically 1. Okay? So this function is going to be AT is equal to A0 times 0.9999879t. Now there's an easier way to do this using half-life. You can have, I believe it's, trying to remember, I believe it's AT is equal to A0 times 0.5, because your base is half-life. And I believe it's T over H, time over half-life. Okay? And so that's another way you can work this kind of problem. The time and the half-life, though, if the half-life's in years, your time needs to be in years. If your half-life is in days, your time needs to be in days. So they have to be the same unit, and your amounts have to all be the same, either grams or kilograms or whatever. So let's go ahead and work this problem. There's not one like this on your homework. Oh, there's not a problem either. Okay, compound interest. This is a formula you need to memorize for your test, for your final exam. It's AT, and that's at the amount at the end of the investment, is equal to P. P is your original investment. 1 plus the rate, which is your percent divided by 100. So if it's 7%, it's going to be 0.07 is R. N is the number of compounds in a year, and then N times T is again the number of compounds, and T is always years. So that's something you need to memorize. There's that, and there's a continuous interest formula that we're going to have in a little bit. So Sandy invests $10,000 in a savings account, earning 4.5% annual interest compounded quarterly. What I tell students to do is to list the values. So you have A, you have P, you have R, N, and T. Okay, and what are you given and what are you left that you have to find out? So invest $10,000. The amount she invests is the principal. Okay. It has 4.5% annual interest compounded quarterly. So the rate is 0.045. Remember, you have to move that decimal over 2 places. This quarterly is your compound word, so that's going to be 4. Could be, say, monthly, could say daily. Look for a word that tells you what your N is. What is the value of her investment after 3.5 years? So time is 3.5. So to set this up, and we're looking for A. So we're going to look for A at 3.5 years is equal to 10,000 times 1 plus 0.045 over 4 to the 4 times t power. And t is 3.5 years. So, okay, let me take that t off. 4 times 3.5. Okay. So whatever 4 times 3.5 is, that's the power you're going to raise it to. So I don't have a calculator right in front of me, so we're just going to go to the next slide where they have it calculated out. But that's how you would set that up. And I do like to list the variables. I think that helps. So we've got that all. They've located all the variables and all the things, and they put them in the formula. Okay. So that's 1 plus 0.045 over 4 is 1.01125. 4 times 3.5 is 14. So do this part first in your calculator. Do this part raised to the 14th power and then multiply it by the 10,000. Some people do it first and they end up trying to raise the 10,000 to the 14th power too, and it's only this part that's raised to the 14th power, just this part here. So do that, then multiply by 10,000, and you'll get this as your final answer, $11,695.52 in 3.5 years. Okay. So now, 9 months after depositing $520 in a monthly compound savings account, Frank checks his balance, finds the account has $528.84. Being the forgetful type, he can't remember what the bank's annual interest rate for his account is and sees the bank is advertising 2.5% for new accounts. Should he close out his existing account and open a new one? So we need to figure out if the rate they're advertising is better than what he's getting. All right, so this time we know the amount at the end. We know the initial amount. So if we were going to list what we know P. Let me go back. Okay, we know P. The amount he originally invested was $520. We know the amount at the end was $528.84. His annual interest rate, so his rate was 0.0. No, he doesn't remember. That's right. He doesn't remember this. That's what we're going to end up looking for. It's only 9 months. 9 months is 9/12 of a year, or 3/4. So our time is going to be 0.75 years, because remember it's always in years, or 3/4 of a year. Annual interest rate, it doesn't say how many compounds, so I guess we're going to figure out the number of compounds is just 1. No, it does say monthly compounded, so it's 12. Monthly compounded savings account. So now we're trying to find out the R, the rate for this. And that's maybe a little more complicated, but we can do it. So let's go to the next page and look at the problem as it's put into the formula. Okay. So we have 528.84 is equal to 520. 1 plus R over 12 to the 12 times 0.75. Remember, we're trying to find the R. Okay? So first thing we'll do is divide by 520. Okay? Simplified the exponent. What they did was they multiplied the 12 times 0.75 and got 9. Okay, divided by 520 and you got 1.017. Okay? Now, this is we're going to do the 9th root of both sides. Okay? Take the 9th root of both sides. That means you're going to say in your calculator, when we know logarithms, you don't have to do this. It's a little easier with logarithms. But what you're going to put in your calculator is 1.017 to the 1/9 power. That's going to give you the 9th root. And you should get this number, 1.001875. Okay, then you're going to subtract 1 from that. And then multiply by 12. And your rate is 0.0225, which is 2.25%. So if he switched to 2.5%, he would get a slight advantage. Probably not a lot, but he would get a little bit. His current account is not paying as much as the advertised accounts. I don't know why he couldn't just go and say, I need that current rate. But anyway. All right. E is defined to the value as 1 plus 1 over m to the m power. And we're not going to worry about that. It says m approaches infinity, I believe is what this means here. That has these strange symbols that are just come up strangely on the PowerPoint. But what really matters is that this E has a value, and that's it. It's a long decimal like a pi is. And so usually 2.7183 is enough. Your calculator, if you're using a calculator, has an E button on it. It's probably somewhere around the LN button. Either over it or there's an E button with the LN over it, depending on the calculator that you're using. Okay. This is used in continuous interest. And so this is the second interest formula you need. The amount at the end of a certain time of investment is equal to the principal times E raised to the RT power. There's no number of compounds because it's compounded continuously. So if Sandy, last seen in another example, has the option of putting her $10,000 in a continuously compounded account at 4.5% interest, what would be the value after 3.5 years? Okay, so again, we're going to put this in the formula. P is at 10,000. We want the amount after 3.5 years. We have E to the R times T, so that's 0.045 times 3.5. That's 10,000 E to the 0.1575. Again, put this in your calculator. Find the E button, raise it to the 0.1575, then multiply it by 10,000. And you will get $11,705.81. Okay, that's a little bit more than the example 3 where she was $11,695. I guess it was about 10. This is about $10 more. So continuous compounding at the same rate for the same amount of time will yield a little more money. Okay, that's the end of section 7.2.